Good afternoon. Welcome to Krishna's classroom. Next, we introduce the concept of compact sets. Because they form a very special class of sets with some fascinating properties. In fact, it would not be inappropriate to consider them as the generalizations of finite sets. At least intuitively, this is what it appears to be. And many results on compact sets can be guessed or foreseen with this kind of intuitive vision. Now, before we start compact sets, a lot of background work has to be done. First of all, we talk about what are called indexed sets. So I can say that it's a generalization now. Now we need the preliminaries. Now, in a metric space, what you call a compact set is the one for which every open cover has a finite subcover. That is the definition. I am not going to write this definition at this stage, but later we will see this. Therefore, a lot of things are involved. What exactly you mean by an open cover? And then, of course, you can talk about finite subcover. And this requires what are called the indexed sets. So let X be non-empty and an index set I. This need not be the natural numbers or anything. It could be I which is non-empty, and then you have mapped from I to what is called the power set on X. This is the power set on X, that is the set of all. So, if you have I belonging to I, then we have AI is an element of, is a subset of X. That means it is an element of, that is AI. So associated with each I in the index set, you have A. So this is what you have. So each I belonging to I, you associate with it a set AI, that is the indexing of the set, and which is an element of the power set, class of subsets of Now this family we write as the collection AI So this is the index class of sets. Now, please do not think that I runs over only integers. Okay. So the collection I may be finite, countable, or uncountable. As we shall see in the examples. Now we recall that a sequence in X is a function from a set of natural numbers to X. So X is the map from X to X, and we denote this, therefore it is actually Xn. N, but conventionally we as these are all the preliminaries as Xn, that is this is the conventional way of writing it. Now we look at the examples. Are defined or are defined equal to the set of where R belongs to that is the intervals of this form minus R to R. This is one example, or we shall write this as JR. This is written as JR for R belonging to Another example is take x equal to R2, and on this we will define CR, let us define as R square. So we take this as now we take R belonging to so we write this as CR now you see that both these are uncountable collections, okay, and there is no reason why it should be an open set. I mean, these are all open sets also, happen to be so, but they are not necessarily this is required. Three, you can even write x equal to R with define to be the collection I'll write here to avoid that same note. Where R belongs to set of all rationals. Now this is again a indexed family of subsets. So these are the examples for indexed family of sets. Now on every set you can define number of sets. Okay. Now we introduce the notion of what is called an open cover. Let X be metric space. Therefore, we can talk about open sets or closed sets on that, because those terminologies do make sense since we are in a metric space. A family of UI I belonging to some index set is called an open cover. An open cover what I want to say is want to introduce a set here and then talk about. Let A be a subset of the collection of subsets, a family of UI for I belonging to a certain index set I is called an open cover A if the following: 1, UI is open, for each I belonging to I. 2, A is contained in union I UI. So these are the sets I am talking about. Okay, so these are all open sets and provides with a covering for A in the sense that A can be enclosed inside the union of these UIs. Now, one remark that is in place is this. Subset of X. So this is what you have. You have got, this is the metric space X. A is a subset. Now you see you have a collection of sets. This is A. So A is enclosed inside UI. So this is each UI. This is the scenario that you have. Okay. If you want, you can display this. Okay. If J contained in I, J is contained in I and A is contained in union then we say that the collection AJ is a subcover for A. If J is finite, then and subcover, then it is called a finite subcover. Now say if AJs are open, naturally it's a open cover. So a open cover for A and a finite subcover for A and further a finite subcover, finite open subcover. So you have got a cover, an open cover, an open subcover and a finite open subcover. These three things are there. Now let us look at some examples. So that will give you, help you to fix the ideas. First example, you consider this one. The interval 1 by n to 1. N belonging to n. N greater than or equal to is an open cover for the interval now how does this look? One. Now if you look at a typical element of this is this. See, this is the set that you are talking about. N points are not included. It's an open set you are talking. This is the set. Okay. And suppose this is 1 by. Then this is the a typical member of this. So you have got an equal to a equal to one. Now my claim is that a is contained in the how do you prove that? I mean, I am not going to write down the proof. The proof is very simple. You see that given any x belonging to there exists such that 1 by n is less than x, which implies x belongs to that's a proof. Okay. Therefore, the entire interval, open interval 0, 1 is contained in the union of these sets. Right. Although in this case, of course, each an is contained in the interval 0. Make some observations on this. The open cover does not admit a finite why it is so? After all, if to see that 1 by m is less than 1 by n, then of course you can simply replace this by this. But then, see, that is n is less than m. Nevertheless, it is not possible cover 0, 1 a finite the reason is if you take a finite subcollection 1 by n1 1, 1 by n2, 1, etc. 1 by nk1, then you can find an m among all these n1, n2, etc. nk such that m is greater than. So you can just put it in in just one of the intervals. But what happens? Still a lot of elements of 0, 1 are left out. It's a very interesting example because if you take any subset of the type a to 1, a greater than 0, this can be put inside one by m1 for m by choosing this follows from Archimedean property. But you see that if you want to include every element of the interval 0, 1, you need an infinite collection. A finite collection is not going to include this. And that's a very fascinating thing about this example. Now, another observation that you want to make is second observation is this. Suppose we adjoin two open intervals one containing 0 and the other one, say one, then the collection, the open cover for 0, 1 given by union n equal to 1 to infinity union j0 union j1. Look at this one. This actually contains and provides the closed bounded interval 0, 1 with an open cover. Okay. has a finite subcover. That is easy to see because what you are doing is this. This is 0, this is 1, and you have got these sets. This collection is there. Then you have adjoined to this another an open set J0 and an open set J1. Now it's quite easy to see that, suppose equal to some A, it is so. Okay, then then you see that you can easily provide with a choose M such that J0 union J1 is a finite open so you see that when you did not have 0 and 1 in it, especially when 0 was not there, this particular cover did not have a finite subcover. But the moment you brought in those 2 points and added 2 more open sets, one containing 0 and one containing 1, then we have a situation where you have a finite subcover for this set. Okay. I'll suggest some other examples like exercises. A So you note that AN is equal to the interval 0 to. Now you see the situation is now changed from the end 1 0 to 1. So a similar argument as we did before gives you or proves that there does not exist a finite subcover. So this is a cover for AN, but this cover has now the second example. Consider this one. Well, this is actually, if you compute this is the interval. So AN in this case here you have to take N now this collection gives a open cover, but it has no subcover, no finite subcover. Now the next example is this. We take that is the fourth example is this. Consider this collection. So this collection, an open cover R and has no finite subcover. That's our experience of working on some subsets of R. And one observes that if you have an interval which is open, so if you have an open interval AB, open cover, no finite subcover. So also the whole of except if you include one can construct an open cover no finite subcover. So our focus is on sets for which every open cover has a finite subcover. So now you can see that it's an awful lot of restriction that you are clamping. Okay. So some of the questions that we are going to ask immediately are: which sets have this property? At least on R, which subsets have this property? Okay. Clearly, you see that any finite set we take has this property. Okay. So we will just keep that in mind. Now you can, another example. Given XD a metric space, for each x belonging to X, P bxr, so r positive hence for any subset of it. Okay, right. Now, using continuous functions, we can construct a open cover for a given set. So, let next example. Metric spaces. Let be a continuous function from x to y. So, given epsilon positive, we shall construct an open cover x using the how do we do that? In some situations, this is very helpful. You have x, y, f is a map, and you see that x gets mapped to x. Suppose f is odd. We assume f is odd. Then what happens? Given any y, there may be more than one x. Such that y is equal to f of x. Now consider the collection B Y epsilon for the given epsilon positive. Epsilon positive. This provides Y open cover. Now consider the following. For each, now we shall use continuity. What does it say? Given epsilon, there exists a delta positive such that, and this delta, of course, delta depends on epsilon and course x or y. Such that B f of epsilon. Now this is the definition of continuity. Given epsilon positive, where y of course is equal to now what you have to do is consider all the bx deltas. It is true that it may not be the same delta in all cases, but given an epsilon, you can find a delta such that bx delta is mapped into by delta, and bx delta is an open x. So now you look at this collection. This delta would depend on epsilon and y. Okay. This collection for and run over all the y belonging to then this is an open cover for this is an open cover for X. Oh, one can write here for every x belonging to what we have is y is equal to fx. Open count. Or x is contained in now take the next example. Consider A equal to 1 by n union 0. Then where x is finite collection of A alpha which is a finite subcover I think that also needs some example. So note that, observe that. Limit n tending to infinity 1 by n equal to 0. So 0 is the limit point. That is 0 is the Therefore, what happens is that if you choose an open set containing 0, say any open set zero contains that is for some M, the entire collection is contained in so all that you need is now take care of. So it is choose alpha, which contains which contains the elements 1 by 2 finitely many with this property. Hence, this collection has a finite subcover. So, somewhat striking feature is that this set contains all its limit points. Okay, so the given A contains, so observe that A contains all its limits. Remark. Whereas, see, if you were to consider only 1 by n, if B equal to, then there exists an open cover for B which does not finite subcover. Now I think we will end this talk with the definition of compactness. A subset where X is a metric space. Is said to be compact if every open cover of K admits so if every open cover has a finite subcover, that's the important thing. Every open cover has a finite subcover. Not that just one open cover has a finite subcover, but every open cover has a finite subcover. Then you say the set is of a special type and it is called a compact set. Now what we want to explore now further is is it possible to characterize such sets through the properties? This is one question. Okay, right. And what about functions defined on that? These are all the general questions that we would like to ask and prove some general result regarding this. Now already some insight you would have already got. That is, it contains all its limit points. So if all the limit points are not there, then of course you are not going to get compactness. And if the interval that we have looked at, if it is closed, if it is not closed, because the endpoints are not left out, then you are not going to get compactness. If it is unbounded, you are not going to get compactness. And these are some of the observations that we have made through these examples. Now, what we want is to explore and do more mathematics on these class of sets. Thank you very much.